Hello, my name is Lexi Goldman, and in today's video, I will be reviewing my calibration curve mastery assignment. The first concept is accurately describe the purpose of a calibration curve. A calibration curve is the measurement of a dependent variable as a function of a known independent variable. A calibration curve can be used to demonstrate the relationship between the independent and dependent variables in an experiment. A calibration curve can also be used to determine the precision of data and to determine an unknown value. The second concept is accurately define and identify dependent and independent variables. An independent variable is the variable that is changed or controlled in a scientific experiment in order to test the dependent variable. The independent variable causes a direct change in the dependent variable. In my experiment, the independent variable is concentration in drops per liter. The independent variable is listed on the x-axis. The dependent variable is the variable being measured or tested in a scientific experiment, and it is dependent on the independent variable. In my experiment, the dependent variable is absorbance, and it is listed on the y-axis. The third concept is appropriately design an experiment to collect data for a calibration curve. For my calibration curve, I used the absorption spectroscopy experiment, in which I determined the concentration of red dye in red Kool-Aid. I created 4 solutions of known concentrations. 20, 40, 60, and 80% were the concentrations of dye in each solution. I had to convert these percentages to the concentration in drops per liter. I did so by taking the percentage and dividing it by 100 and multiplying that by 90, which is the concentration of the stock solution. I then had to use the equation C1 times V1 equals C2 times V2 in order to find how many milliliters of dye were necessary to complete each solution. C1 is 90 drops per liter, which is the concentration of the stock solution. C2 is the desired concentration of each solution in drops per liter. V2 is the desired volume of each solution, which is 5 milliliters. I also used water and dye as controls. 0 drops per liter is the concentration of water, and 90 drops per liter is the concentration of the red dye. After making each solution, I measured the absorbance of each solution. The independent variable was concentration in drops per liter. The range was 0 drops per liter, which was water, to 90 drops per liter, which was the dye. The range on the calibration curve is 0 to 100 drops per liter. I increased the concentration by increments of 20%, which was equivalent to 18 drops per liter. The dependent variable is the absorbance. The fourth concept is accurately describe how to create a calibration curve with experimental data. I will complete this concept when I complete the calibration curve at the end of this video. The fifth concept is accurately describe how to use a calibration curve to determine an unknown value. In order to determine an unknown value, the equation of the trend line on the calibration curve can be used. To do so, we must substitute a known value into the equation. In turn, we will be able to find an unknown value. I will demonstrate this when I complete my calibration curve. The last concept is accurately characterize the precision of a calibration curve. The precision of a calibration curve is determined by the r-squared value. The r-squared value represents the proportion of data that is predictable by the best fit line. The closer the r-squared value is to 1, the better the precision. The closer the r-squared value is to 0, the worse the precision. In this video, I will be demonstrating how to make a calibration curve. To make my calibration curve, I will be using my dye solutions data. The independent variable is concentration in drops per liter. This will be listed on the x-axis. The dependent variable is absorbance. This will be listed on the y-axis. To begin, I must highlight all of my data, go to Insert, Charts, and Scatter. Then I must label my axis for concentration, which is the x-axis, and the axis for absorbance, which is the y-axis. After doing that, I can also change the title to include concentration. Now that I've completed all of the labeling, I can add the trend line, along with the equation and the r-squared value. My r-squared value is 0.9853, which is relatively close to 1, meaning that my data is pretty precise. I can also change my axis range, so that it doesn't go down to negative 0.5. That way the data looks more cohesive that way. There we go. Now that I've done all of that, I can use my equation to determine an unknown value. To do so, I will be using my drink solutions data. My absorbance is here, and that is what is known, but I do not know my concentration. I can manipulate this equation over here to get it where it's x equals y plus 0.0391 divided by 0.0206. Then I can substitute these absorbance values into that equation. I will do equals, parentheses, highlight the absorbance value, which is the y value. Then I will do plus 0.0391, close the parentheses, and divide by 0.0206. This gives me the concentration. I can drag this down all of the boxes to find the concentration of every absorbance value for every solution. That is how to create a calibration curve using independent and dependent variables, how to label the axis of both, and how to find the equation and the precision based on the r-squared value, along with how to use this equation to find the concentration. Thank you. This concludes my calibration curve mastery assignment. Thank you.